Welcome everybody. Thank you very much for coming to the Oxford Energy Network seminar. Before introducing this week's guest, I'll just say a couple of general things. So first of all, my name is Tina Fawcett. I'm the convener of the network. Normally we have my colleague Karen, who's the coordinator and who manages the tech. So we're hoping that things are going all right. And apologies if I need to sort of step in at some point and panic at the computer, but we hope that's going well. To mention before we start next week's seminar is going to be by my colleague Yvan Fan from the Environmental Change Institute, and she's going to be talking about exploring digitalisation's footprint. So that will be in this department. I think it's the upstairs room next week, same time, and then we've got two more talks finishing in week 8 with a sort of celebration of what Oxford chemistry has done for the energy transition. And that is just before there's going to be the first Good Enough lecture, which is again a celebration of chemistry at Oxford with a sort of Nobel Prize laureate coming to speak at St Cat's College on the 3rd of December. So that's all very exciting. Just one more event to mention is on the 11th of December, it's the Oxford Energy Lunch, which the Zero Institute will be running. It's going to, again, that will be hosted in this building, so you should be seeing information about that. And I suppose finally, if you were at Oxford Energy Day, it's on the 24th of September, and we've now got a gallery of photographs from the day online. So if you were there and you haven't seen any pictures of yourself, you might find them online. So we've got pictures of the presenters and people standing in front of posters and doing a bit of general chit chat. So that's quite a nice resource for those who are there. Right, so now to pass over to the main event, I'm delighted to introduce Jesus Lizana, who's an associate professor in the Department of Engineering Science. A lot of us in the energy team in this building have worked with Jesus on a number of projects, and really pleased that he's here today to talk to us about his work on heating and cooling. So he leads the heating and cooling research in the Zero Institute. He also does a lot of teaching on MEng and MSc courses. There's doing lots of really interesting initiatives within the university and also working outside with lots of partners. Jesus is here now, but he's had a very international career, working across, I think he said, Spain, Germany, Portugal, and now the UK, working in both academia and in professional roles. So we're really excited to have him here, and I'll let you begin your talk.
Fantastic. Thank you very much, Tina. Thank you for coming. I hope for an interesting lecture about zero carbon heating and cooling. As Tina said, I'm a member of the leadership team at the Oxford Zero Institute, where we address research for the 5 main pillars of the energy system on generation, conversion, distribution, storage, and energy use for the 4 main energy sectors: the power sector, transport, industry, and in my case, leading on most of the initiatives on the building sector. We are going to talk now. A building sector which is responsible for 37% of the total carbon emissions. This is the current situation, 27% related to the building operations, the carbon, and 10% related to the materials and construction process. A situation that didn't change a lot in the last years. The situation, according to the recent report from the UNEP, is awful. So we are not even close to the 10% of the path to decarbonize the building sector, and probably one of the most difficult sectors to decarbonize. So in this presentation, I will address 4 points. The first one is, what is a net zero building? There is no clear definition, and I will try to show you the recent progress that we have right now, or what we need to achieve to decarbonize the building sector. Then I will talk about the role of building services engineering and academia to support the decarbonization of the building sector. And later, I will try to explain or to showcase the limits of the current practices of the building sector, the current best practices, where we are right now. Is this possible? It's only about to deploying the best practices, or do we need to achieve something else? And I will finalize the presentation with the 4 key projects, key research innovation in which we are working for heating and cooling. So I'm going to start with the first question. What is a net zero building? I try to ask this question to my students. Is this just about installing photovoltaic panels? We can be net zero, right? Right panels, electric battery, and we can completely decarbonize the building sector. Can we do this? Is this officially a net zero building? Of course, the question is no. And there is a recent report from the Green Building Council explaining why we need to achieve a reduction of energy demand by more than 60% in order to balance renewable supply with demand. Of course, understanding this, there are many definitions of a net zero building. There is no one single definition. This is it's not a problem. It's an interesting discussion. I think the situation now is slightly better than in 2023, but I will try to talk a little bit about them and focus in the one that I consider the most important one right now. So with the Green Building Council, the Green Building Council in 2019 established a framework, about a qualitative framework about the meaning of what could be a net zero building, but without any specific key performance indicators or specific target that we need to achieve. The International Energy Agency in 2021 established a really interesting definition, the concept of zero carbon ready building. So this is not about being net zero now. It's about to prepare the building to be net zero. Something really interesting. So the concept was like, we don't have to decarbonize the building sector right now. We only need to prepare. Then in parallel, we have the Energy Performance of Building Directive from the European Union that is responsible to addressing all the national standards that we have in different countries in Europe, with a new terminology for a net zero building, the zero emission buildings. Previously, if you remember, the concept was a nearly zero energy building. And now it's focusing on carbon emission, and somehow is integrating some of the concepts previously defined by the International Energy Agency. But the one that I find the most complete definition is the one that was recently defined in the UK, is the UK Net Zero Carbon Buildings Standard. This is a new definition, and my view is the most complete definition of what is a net zero building. This was a new standard where the pilot was published in September last year in agreement with many different institutions from the UK and completely aligned to the UK net zero strategy. So it's UK oriented, the definition of this net zero building concept. In this standard, we find the most complete definition of what is a net zero building. The standard defines specific limits, targets, and reported requirements. And the most interesting part is that to be a net zero building, we don't have to emit zero carbon emissions. And this is the main concept I would like to transmit today. The limits and the most important limits that we need to achieve will be related to the upfront carbon, the embodied carbon that we use in buildings, and the operational energy or the energy use intensity. Then we have a different indicators, different limits that we need to address, that somehow they are easy to address, but the two most difficult one will be these two. Then we have a target of on-site renewable energy generation, a minimum contribution of renewable energy that we need to achieve from every building. The reporting requirements are very associated to, of course, we need to report the carbon emissions that we have for this specific building, but there is no requirement. With this framework, what is the role of building services engineering and academia in achieving net zero? We have a large portfolio of solutional technologies in the building sector to provide electricity, to provide heat, and to provide cool. Technologies that we can classify in the 5 main pillars of the energy system, specifically for the building sector. And of course, we can quickly identify what are the most promising technologies, right? When we look at heating and cooling, of course, when we compare the efficiencies of all these technologies, heat pump is winning. Heat pump is the most promising technology and will be the most important technology to decarbonize the building sector. And this is something, all these best practices, existing best practices, is something that we try to address or to teach as an academic institution. This is something that we started last year, introducing new courses in the undergraduate programs and in the University of Oxford, different lectures and MSc programs, creating a new field program in which we are working right now, and in the future, executive education, and even creating educational resources. And the most important action initiative that we were leading was the university competition. We would like to engage students to try to start thinking about what are the radical innovations that we need to address in the building sector to decarbonize. And there is no better way to do that than through the academic competition. This is the UK team. that participated, different field students from also participated in the European competition on zero carbon data centers. And this is a reminder that the 21st of November, they will be presenting the winner project of this competition. And this activity was highly recognized. All the Zero Institute members that participated, they were highly recognized by different awards last year. The TIPS Award 2025 in Learning and Development, the ASTRAI 2025 Award for Zero Carbon Education, and also the 2025 MPLS Teaching Award. But even the students, the first year they participated, we got 2 awards from 3 teams that participated. The first prize for the European competition on zero carbon data centers, and the Rising Star Award by the Global ASTRAI competition, something of which we are very, very proud. Of course, this is our role as an academic institution, but are the best practices then enough to achieve net zero? It's only about teaching and showing the best practices. Traditionally, I try to explain this with the case of Wolfson College. I am a member of Wolfson College. As you may know, this was one of the major decarbonisation projects at Oxford with an investment higher than 10 million of investment. But of course, this is one simple case. You may say, okay, but this is not representative of the UK. But today, I'm going to change the topic. I'm going to pick up the 10 best practices in the building sector in the UK to try to compare where we are with the best practices in comparison with this standard, with the requirement that we have from this net zero carbon buildings standard. This was a project that we had this year from an MSc student, Jessica Ibanez, that initially selected a sample of 10. She's working now in a much bigger sample to try to characterize the best practices in the building sector, and I will showcase these tentative results. The 10 case studies were selected according to the most recognized buildings who received specific awards or recognitions in the UK as examples of best practices. We compare the performance of all these buildings across 2 main indicators, the embodied carbon and the final energy consumption of energy use intensity. The 2 most important indicators that I mentioned previously that we need to address for the new UK net zero carbon buildings is standard. Let's start comparing first the final energy consumption of these buildings, the energy use intensity, with the target that we need to meet to be a net zero building. And you may see the target for 2025 somehow is very close. Most of the case studies are below this threshold, this consumption, which is fantastic. Some of them are not. How is going to change the situation with this standard by 2035 and 2050? The requirement will be much stronger. Here, what we can see is that even the best practices right now are close, but the effort that we need to achieve is not huge. It's possible. Even with best practices, with a little bit of improvement, we will be able to meet this requirement easily. It's not a big challenge. Let's try to compare it. Well, one question. We have buildings here, so divided according to if the building was measured, real data, or if the building was simulated. We identify the building that is closer to meet the threshold by 2050 in the figure. From the blue colors of the building, right? Do you know from where is this building? Who is the client of this building? University of Cambridge. Oh, we can do better. Let's compare now the embodied carbon. The embodied carbon situation. This is going to be the most difficult one. Right now, according to the best practices in the building sector, the embodied carbon is between, in some of the cases, between 400, 600 kilograms of CO2 equivalent per square meter. But let me show you the situation of the target, the limit that we need to achieve by 2035 and 2050. This is almost impossible. This probably will be the most important challenge that we will need to address in the building sector, how to decarbonize the embodied carbon when we design and build buildings. So it's clear to me with these 10 examples that the best practices alone will not get us to net zero in the building sector. This is where I am leading the Zero Carbon Heating and Cooling Program at the Zero Institute, working on these radical innovations that we need to implement in the building sector to decarbonize it and to reach net zero. Mainly working in 3 main areas on heating decarbonization, working on new materials and technologies to decarbonize the building sector, on climate risk analysis, generating and analyzing new climate data sets and information that we can use to understand much better how we need to design buildings for the future climate, and on cooling, more focusing on climate adaptation, how to prepare for a changing climate. By heating and cooling in the building sector, you only need to see this picture. 50% of the energy demand in the European Union is for heating and cooling. Most of the energy demand that we use for building is thermal, it's not electricity. 30% is associated to, in Europe, is associated with space heating and water heating, mainly in buildings. 4% is cooling, not only for buildings or for other applications. And of course, there we have medium and high temperature heating for industry. But heating is the most important energy use in Europe. And a word, of course, not working alone, working more than 10 years working on this topic, as Tina mentioned, previously working in the building industry. Later I joined academia, and I was working across Spain, Germany, Scotland, Portugal, Spain again, and from 2021 in Oxford, collaborating with more than 60 international institutions, with many academic publications with all of them. And I will focus on the three most interesting innovations in which we are working right now. These are the key radical innovations on heating specifically that we have with three projects. The first one is associated to hybrid indoor design conditions. This is a project that I started with the European funding with my Marie Curie project in 2021, and we continue working with this. The second one is about optimal sizing and control of heating systems. This is EPSRC funding for the development of an open building energy simulation software to improve how we size heating and cooling systems. And the last one is about a better auxiliary system for heating. It's a project about low temperature thermochemical reactions for heat batteries. Let's start with the first project. It's quite clear that thermal comfort is not temperature. This is something that we overlook completely when we are calculating or sizing heating systems. We have 6 thermal comfort variables that we can use and play with them to create a comfortable environment. 4 environmental parameters: drivable temperature, mid-range temperature, relative humidity, and airspeed, and 2 personal factors: the metabolic rate and the clothing insulation layer, the amount of layers that we are wearing. The most important key message here is that by every degree Celsius that we can modify the drivable temperature, we can save between 5 and 10% of the energy demand for heating and cooling. This is huge. How can we do that? First, now we need to talk about psychometry in order to explain this. Psychometry is the field of engineering that studies the physical and thermodynamic properties of the moist air as a combination of dry air and water vapor. And the psychometric chart, this plot that we can see here, is an essential tool for designing and calculating heating and cooling systems. It represents the hydrothermal properties of the humid air in a graphical form. And understanding 2 variables, we can automatically obtain all the different physical and thermal properties of the humid air. In this figure, the red point, you see this red point below. Let me try to indicate this with the laser point. In the horizontal axis, we can see the drivable temperature. In these curves, we can characterize the relative humidity. In this horizontal line, we can characterize the absolute amount of water into the air, and this will be the enthalpy value. And this pink area here will be what we traditionally call the thermal comfort zone. How do we calculate heating system? How do we size a heat pump for your new home? We define the indoor design conditions, and we establish the outdoor design conditions. For Oxford, this value is minus 5.5 degrees Celsius. How many hours in a year do we have minus 5.5 in Oxford?
0 most years.
Few hours. I mean, this value is traditionally obtained by a percentile of historical temperature. It's the worst case scenario that we may have and the system should be able to meet, to be able to heat that home for that particular scenario. But it's very strange situation. What are we doing in this project is, it will be super interesting if we can move down the thermal comfort zone without sacrificing comfort, of course. Why? Because you remember, by every degree Celsius that we can decrease the thermostat, we can save between 5 and 10% of energy. That's huge. How to do it? Also, if we decrease this set point, we also will decrease the capital cost for the heat pump, because we are going to reduce the peak load. This is also another benefit. So the potential benefits will be a reduction of 30% of the energy demand and a reduction by 10% of the heat. How we can do this? Please don't try this at home. It can be dangerous and could even spark a bottle, a thermostat war, something that we saw in the town hall last year. We, even with some members of one member of the cabinet said, clearly someone has lost their temper and thought, right, I'm going to solve the problem right now by padlocking. Please take care if you try to do this, but I'm going to tell you how to do it. This is something that in which we are working at the Zero Institute, and it's working fantastically well. The first step, what can be measured can be controlled. So we need to measure thermal comfort, not only temperature. And this is a device in which we were working last year in order to measure all the thermal comfort variables. With all these thermal comfort variables, instead of measuring a specific temperature that we don't know if that temperature will be comfort, what we are measuring is the predicted mean load index. An index that basically tells us what is the thermal comfort sensation from -3 to +3, where -3 in this figure will be cold situation, +3 will be hot, and the neutral and perfect thermal comfort zone will be 0. This is not new. This was created in the 70s by Fanger. We are not using it, and the potential is huge. Something really important that you need to understand if you want to use this index is that with the prediction mean load index, even at the neutral comfort zone, when the index is 0, between 5 and 10% of people will be satisfied. This is really important. So even at the perfect thermal comfort situation, people will complain. Understanding this, what is the next step? We need to tell these people, stop complaining. We need to empower the occupiers and tell them that it's okay, the thermal comfort sensation is fantastic. We know that there are between 5 and 10% of people dissatisfied, but there is a 90% that they are okay. So it's quite important this, because most of the time we change things only because one person is complaining. So as soon as we inform, then is where we can play. We can play scientifically and well. Then is when we can start moving from the classical approach that we use to provide heating only by controlling the drivable temperature. As you can see in this figure, now we have the psychometric charge, the thermal comfort zone, and also the values for this index, where the white area that will be what we call traditionally the thermal comfort zone will be when the index is between -0.5 and +0.5. And from there, it's going to increase to slightly warm or hot, or slightly cool, cold and cold. How can we do then this decrease in the drivable temperature without sacrificing comfort? We need to start playing with a second variable. In this case, will be the mean radiant temperature. The mean radiant temperature is the temperature emitted by the surfaces. Traditionally, we don't touch them. Well, not when we have an underfloor heating system, the mean radiant temperature will be slightly higher, but we don't measure it, we don't control it. What is interesting is that now if we combine, instead of only convective heating with a traditional radiator with radiant heat, for example, with an infrared heating panel that they are becoming really interesting now, we can start controlling these two variables together. And we can create a perfect comfort environment at 18 degrees Celsius of drivable temperature and at 27 degrees Celsius of mean radiant temperature. And of course, we can apply the same concept to cooling. Even this is something that in most of the new university buildings in Singapore, they are implementing right now. For cooling, the the concept is slightly similar. So we move from in this figure, we can see the potential energy savings with the set point temperature and the traditional, the 21 and 24. So for heating, what is the opportunity? Introducing a second variable, the radiant mean temperature. For cooling, introducing a higher ASP will be a fantastic solution, because then we will move the thermal comfort zone to the upper zone of the psychometric charge. What is the question that we would like to answer? Of course, there will be an energy penalty, because this system will have a consumption. In cooling, it's quite easy to assume that fans will consume much less energy than a chiller or a heat pump for cooling mode. But for radiant heat, we need to understand how to control and use this properly, and this is where we are working right now. The second project is about it's time to stop over-engineering systems for managing peak loads. I hope that you agree with me here. Why this was never a problem and now it's becoming a huge problem. In this graph, you can see the traditional price per kilowatt of a gas boiler, between 200 pounds per kilowatt, more or less. There was not a problem for buying a bigger gas boiler. They were cheap, gas was cheap, so there was no major concern. So we were sizing for these extreme conditions and we didn't care. Now the price for heat pumps is 10 times higher. So I think we need to start looking back and start optimizing how we design system for managing peak loads. Coming back again to my psychometric charge, this is the traditional approach: indoor design conditions, outdoor design conditions, sensible peak load for sizing the gas boiler or the heat pump. Something that we traditionally don't evaluate is that this peak condition, of course, is happening a few hours per year. But my view is what is really important is to understand the heating load distribution curve. And this robot can help us to understand much better how to structure the sizing of the heating system. This is the 0 Institute building, for example, and we can see the heating load distribution curve and the annual percentile of the year. And we can see how 99 percentile of the year, the peak load, the required peak load will be slightly higher than 75 kilowatts. Do you know how much is the gas boiler installed in the 0 Institute building? Can you imagine it? Close to 100, of course, slightly higher, much higher. What is the traditional approach for heat pumps? Something, for example, that we install in Wilson College. In Wilson College, from the maximum peak load that we calculated, of course, we are going to have a heat pump system, the main system, that is going to cover 2/3 of the total capacity. Why 2/3? Because it's very expensive, so we need to reduce the size. And then we're going to introduce an auxiliary system that, of course, can be gas, but we want to eliminate completely gas, so it will be an electric heater, because the price of an electric heater is close to the price to a gas boiler. It will be 200 pounds per kilowatt. It's much cheaper. The problem or the opportunity is that with the power of smart control, digitalization, EI, we can start controlling the buildings completely different. Now, we can basically define a system that can avoid that worst case scenario. That worst case situation that is going to happen a few hours a year, now we can completely eliminate it. And how can we do this? It's about preheating the building, it's about reducing set point temperatures, it's about installing a smart control system that we can reduce the peak load. And there is a massive opportunity here to reduce the capital cost of the system, and at the same time to increase the efficiency, the signal efficiency of the heat pumps. A common strategy is this one. Even it's quite common in heritage buildings, and this is a typical mistake that I can see in Oxford in many of the heritage buildings that we have found here. This is the 0 Institute with two different operating modes. One, as normal, heating when we are using the building, and not heating when we are not. And the second one is with the heating on 24 hours per day, the whole year. You can see when we keep the heating on, of course, we are going to reduce drastically the peak load, because that worst case scenario where the system is working from minus something to 21 is not happening anymore. But of course, this will have a penalty of an increase in the energy demand for heating. We don't do that. And we can optimize. Before explaining how to optimize this, traditionally for heritage buildings, how they address the problem. They think that they cannot modify the peak load, so they are going to install a heat pump. They want to keep the same supply temperature for the hydraulic distribution system, and drastically they are going to decrease the efficiency of the heat pumps, having an efficiency even below 2, a cup of 2, which is crazy. So why are you investing in such expensive system to keep that operating conditions that are really not efficient? There is another building, even in Cambridge too, a heritage building, where they decided to operate the building full time the whole year in order to decrease the flow temperature of the hydraulic distribution system, so we can drastically reduce the size of the heat pump, the capital cost, but at the same time increase drastically the seasonal efficiency of the system. But again, this is a drastic situation because of course there is a penalty. How can we do this better? Understanding the potential of a smart control, we can start preheating the building only for these extreme situations when it's very cold. And then we can completely have the benefit of eliminating the peak loads, but we have minimum penalty in the energy consumption of heating. This will be ideal. And this will drastically decrease the size and the capital cost for the heat pumps from 2/3 to 1/3, which is huge. So we are reducing by 50% the capital cost for a new heat pump system. Of course, at the same time, it's much more interesting to have a variable flow temperature, a fixed flow temperature. Because if we fix the temperature of the hydraulic distribution system around 55, 60, in order to meet the peak load, that will be super inefficient. What is more interesting is to, in real time, decrease that temperature according to the load that we are expecting, so we maximize the seasonal efficiency of the systems. So control will play a really important role here. But of course, we need to understand this from the beginning, from the design stage. How to start designing new system, understanding the opportunities that we may have if we start installing this smart control system. So this is the project in which we are working right now, how to design an open software to create cost-effective solutions for achieving net zero. Software for the early stage decision-making process, where with a reduced number of input values, we can create a physics-based building model where we can test these smart control opportunities, and we can do a parametric analysis on how we can reduce the size for the new thermal system that we want to install for the building. A model around, I'm very happy to share this slide because we were fighting a lot for the software validation, where we were comparing the software with 40 different cases, with more than, well, in this case, with 6 different professional softwares. We are happy to say that the software is almost validated, achieving the same level of accuracy for the annual thermal energy demand and also for the peak load. So hopefully at the end of this year, we will have this ready. The final project will be about this key message. Investment in an auxiliary system for just 96 hours a year doesn't make sense. Let me explain you this. We can say that this is one of the best practices in heating systems for medium or large scale buildings. We will have a heat pump. Let me move with the mouse. We have a heat pump technology, and we have an auxiliary system. In this case, it's a gas boiler, but let's think it's an electric heater. It will be the integration that we have in Watson coils, for example. And of course, we have here the buffer tank, and this will be the heating return flow. So the heating return flow will come by this way. If the temperature is not enough, it will come to the buffer tank. It will heat the flow. As soon as we reach this point, if we need to heat the temperature more, then we can use the auxiliary boiler and then go to the supply. Or if the temperature here is enough, we can go directly to supply that to the hydraulic distribution system or for hot water. Question: can we replace this auxiliary system that we are going to use only for 96 hours a year for something that we can use to cover peak loads, but at the same time to provide additional benefits to the building?
Hot water bottles.
Jerseys.
Yeah.
Ideas? Okay. This is in which we are working right now. We are working in new thermochemical heat batteries to provide energy flexibility, but at the same time to cover peak loads, to automatically replace these auxiliary systems. because then we can use this extra heat not only to cover peak loads as we are using right now with this SLD system, also to have the opportunity to provide energy flexibility throughout the year. In thermal energy storage, we have a large portfolio of materials for sensible heat, latent heat, and of course, thermochemical heat reactions. Traditionally, previously was working a lot with latent heat storage, many benefits, but many limitations specifically related to the power that we can deliver with this material. And now what we are focusing is the thermochemical heat storage, maybe for two main benefits. The energy density is much higher, and at the same time, we can have almost negligible heat losses if we design the system properly. Something that with sensible or latent heat, we don't have. So we can store heat for long-term periods with almost zero losses. What materials are we using? Sodium acetate-based composite materials. And why? Because they have a fantastic operating conditions for heating, for low temperature heating. This is what we want. So zero carbon heating means low temperature heating. If you continue having a high temperature system, it will be not efficient. Why this material is so promising? We can charge the battery even at a temperature of 30 degrees Celsius. And in the discharging reaction, we can reach a delta temperature more than 20 degrees Celsius, reaching a maximum temperature close to 50 degrees Celsius. Operating conditions that are perfectly aligned with the heating demand in building. Where we published a proof of concept in 2024, and now we are working in a thermochemical reactor design where we can exploring how to integrate these materials into an auxiliary system, what we call traditionally as an auxiliary system, but not only for covering peak loads, also to provide heating flexibility. These are the three projects about heating decarbonisation. I have one more. I have time, Dina? Yeah. 4 minutes. Yeah, that would be fantastic. I will talk about the work on climate risk analysis and climate adaptation. What is very important about designing for the future is that we need to deeper understand the future climates. We need to prepare to adapt the built environment for the next 30, 50 years. And here is where we are working on citizen science for accurate climate information. We are working with two approaches here. Global climate modeling using the citizen-driven distributed computing infrastructure that we have here at Oxford, the climateprediction.net network, where we are using the computational capacity of computers globally distributed, more than 30,000 computers, and you can sign your computer to be part of this network. And we are using that network to be able to model the highest global mapping of temperatures at 6 hours resolution every 60 square kilometers to understand how heating and cooling is going to change for different global mean temperature rises scenarios. Something also related to citizen science is the use of citizen weather stations. Data from stations from citizen that you can buy a weather station, you can install at your home, and you can share this data in open source, so we can use all this information in order to understand much better the higher temperatures that we find in cities due to the problem of the urban heat island. And in this case, we are focusing on observations, real-time observations, to understand the problem of the urban overheating, targeting a resolution of 1 hour at 1 square kilometer. These are the two concepts. As you can see, this is the expected resolution that we can have with this global modeling of temperatures. And this is what we can see when we start using the citizen weather stations data, where we can clearly understand the implications of the urban heat island in the London climate. And we can see at night urban heat island intensity with a temperature even close to 6 degrees Celsius. But I'm going to focus in this water stream in this presentation quickly. And I am focusing in this one because we just got the last paper published last week. I'm very happy to share this because it was a long fight to get this paper published in Nature Sustainability. Because with this, we published a new global data set on heating and cooling degree days, the largest data set that we can find today, that is able to characterize the climate intensity on heating and cooling globally for 3 global mean temperature rise scenarios. 1 degree Celsius, 1.5, and 2 degrees Celsius, regardless of the pathway that we take to achieve this threshold. This is a dataset with 30 grid maps characterizing the climate variability through 5 statistical descriptors, and I am going to finalize this with the most important key message that we identify from this analysis. This is the traditional map of cooling degree days. As you may know, cooling degree days is an indicator that characterizes the climate intensity globally related to cooling environment. It's not directly associated to energy because, of course, this is only using temperature. We don't know how is the access to the cooling regions, but there is a strong relationship with the exposure and the thermal needs. When we analyze this figure, of course, we can see how in the tropics is where we find the highest values for cooling needs or thermal exposure. That is at the same time where half of the population lives. You can see the density, the global map of density of population and how people in the tropics are experiencing the highest energy demand for cooling. But I really like this way of presenting these maps with the distribution of population by cooling degree days in intervals of 100 cooling degrees. Where we are in the UK, we are close to 100 cooling degrees, so close to here. So right now we have 23% of the global population is living under extreme heat conditions with a cooling degree day of 3,000. How do you think this situation is going to change with the climate change? Let me show you. As soon as we reach a global mean temperature rise of 1.5 degrees Celsius, the situation is going to increase from 23 to 34%, 2.8 billion of people. If we continue and we reach 2 degrees Celsius, the situation will increase even more to 41%. This is crazy. This is unbelievable. So, what is the key message from this situation? What we need to be doing is we need ultra low cost cooling to address this massive challenge. There is no other way. And right now, the target to keep below 1.5 is out of reach. We need to start looking at 2. I don't see right now a clear pathway where we are not going to reach 2. So the situation is crazy. And this is where we are in Europe. So we can clearly see the 2 extreme pictures of the situation. And I'm going to finalize also with a psychometric chart, but with an interesting question. In Spain, I am from Spain, by the way, so in UK, we are here around 100. In Spain, we are close to 1,000. Do you know why in Spain we have the siestas during the hottest hours of the day? People may say that we are lazy.
we wanted to say it, but we couldn't.
People from the North Spain, also, they are complaining that we are super lazy. But the secret is this one. When we decrease the metabolic rate from 1 MET, normal activity, studying, writing, to a siesta, to a nap during the hottest hours of the day, to 0.7 MET, we are decreasing, moving the thermal comfort zone at which we feel comfortable. There is no better way to address ultra low cost cooling than having a siesta. So next summer, if too hot, just remember this presentation, take a siesta, everything will be fine. Final key messages, and I conclude here. Remember, thermal comfort is not only about temperature. Only 1 degree Celsius, we can save between 5 and 10% of energy. And the opportunity is huge. It's time to stop over-engineering systems for managing peak loads. The heat pump size can be reduced by 1/3 if we start sizing system properly. Investment in an auxiliary system for just 96 hours a year doesn't make sense. And here is where high-density thermal energy storage can support peak loads and be used throughout the year, the entire year, for energy flexibility too. And the last one, ultra-low-cost cooling should be the next research priority. We want to fight for climate adaptation, where the siesta probably will be the winner. And this is my presentation. I hope that you enjoyed. Thank you very much for